Okay, here we are, we're looking at a quick guide of how we can do analysis for our rotational inertia lab. I've put up the picture that I had on the Promethean earlier this week. That's my picture at the top of the ball rolling down some incline. And we have our conservation of energy equation right here in the center. So what we're saying is that the energy top should equal the total energy at the bottom. And that's what we see on the left and right hand side of this equation. We have potential at the top, translational kinetic at the top, and rotational kinetic at the top equals the values with the subscript 2, gravitational potential at the bottom, translational kinetic at the bottom, and rotational kinetic at the bottom. Right, that's the assumption that there's no external forces acting on this, so we're ignoring friction and air resistance. We don't know how to put those into this conservation of energy equation yet. We don't have values for how much air resistance is going to affect the ball rolling. We don't know how much rolling friction is going to affect it. So we're just looking at MGH. So again, on the left side down here, you see MGH1. Right, so that's the potential energy the ball has up at the top. It's not moving. It's not moving, so we have no translational or rotational kinetic at the top. And then we have our potential energy at the bottom. Well, when the ball's down here, it's reached its zero height. It's not changing vertically anymore. So that's what we mean by our change in height, is right here. We can call it delta H if we want. So it has zero height at the bottom, so this MGH goes away. And we know at the bottom it is moving. It has both translational, 1/2 mv squared, and rotational, 1/2 I omega squared energy. Okay, so our equation becomes mg, and I'm just going to use h. That's the height of our ramp, whatever we measured, and we made clear last time that we're looking at the difference in height between the center of the mass of the ball where it starts and the center of the mass of the ball where it ends. So here's the center of mass of my ball at the beginning. Let's draw kind of a straight line across. Here's the center of the mass of the ball at the bottom. So really our height is right there. That's the actual height we're talking about. Slight changes in the height measurement could affect our moment of inertia calculation greatly. So that's something you could talk about in your section of the lab report about uncertainty and error. Which measurements, in their uncertainty, which measurements, the height, the speed, which of those measurements contributed most to error, and why do you think so? So we have mgh, that's our potential energy at the beginning, at the top, equals 1/2 mv squared. And by v I mean the velocity of the ball at the bottom. Okay, so that's not really the direction of the vector. On this one, it probably is right like that. But you could have yours coming off at an angle. We just mean the total resultant velocity at the bottom of this ramp. 1/2 mv squared is my translational kinetic plus 1/2 I omega squared. And that's again the final angular velocity for omega. On the right side of my board here, we have our analogs of both linear. This is all linear stuff up here, if you can see where my mouse is. This is all our linear stuff in this column and all of our rotational stuff in this column. This is just copy-pasted from the Hyperphysics website. And so I can see I'm going to be looking at these equations here. I got my kinetic energy for translation and rotation. And if you had taken other measurements like just time, like if you didn't use a photo gate to get the speed, well, we have our kinematic equations, okay? And of course there are other ways we could have found the moment of inertia if we had found a way to find torque in alpha, or angular momentum L, and angular velocity. Those equations also involve the moment of inertia I, so there are multiple ways to approach this lab. Below this set of equations, we have our common moments of inertia for objects. So we're just going to look at the solid sphere for now. That was the first object we all started with. Alright, and so this value of 2/5 mr squared, where m is the mass of the sphere, r is the radius of the sphere, and 2/5 is that coefficient that you can see is different for all of these different types of objects. That value for I, 2/5 mr squared, can be our standard. This is the standard that we calculate with the mathematics. So that's the standard we can compare our experimental value to talk about our error in our lab report. For the sake of my demonstration, I'm just going to care about this part, that coefficient, because I know all of them involve mr squared. The L's on the other ones mean the lengths of the rod. Okay, and some things will involve both the radius and the length, depending on what type of object. We just have r in our solid sphere's moment of inertia. So this coefficient I've highlighted in green, the 2/5, I'm just going to give that the designation k and make up a variable as a stand-in. Because I'm going to calculate the moment of inertia experimentally for a solid sphere, and I don't know if k is going to be 2/5, which is the same thing as 0.4, or maybe I'll get 0.48, or maybe I'll get 0.37, but I'm going to use that variable k to stand in for this coefficient I'm solving for. So what I will show you first is how I can solve for that k. I have my conservation of energy equation. This is really what we're starting with because we could get rid of some of those values that we said wouldn't be present. Okay, namely the kinetic energy before, that goes away. Those are crossed out in blue, and the potential energy afterwards at the bottom, that's crossed out in red. So you can start substituting values in and see how much you can get. We know g, we know the mass, you measured that. You don't have to actually for this, but if you measured the mass, you could substitute mass in. The height, you know, you needed to have measured that if you're using a ramp. Alright, omega and v we get from our measurements of the speed, or calculating the speed using our kinematic equations. So I'm going to rewrite this equation I've boxed in black. mgh, that's all we have initially. I'm going to rewrite it so that it's something I can actually work with, because I have too many variables right now. I have 1/2 mv squared, that's my translational, plus I have 1/2 I. Now I know I is going to be my coefficient, whatever fraction I'm going to get, times mr squared. So I is k mr squared. And so that's my I, right there. Alright, my omega, we said for non-slipping rolling motion. For non-slipping rolling motion, linear speed v is equal to the tangential speed at the edge of the tire, or the sphere. And I know that vt is equal to omega r. That's one of my go-between equations. Therefore, v is equal to omega r. Linear speed v is equal to omega r. And so I have this value here that I'll highlight in green for a second. Right, there's my omega. Alright, so if I can solve this for omega, I can substitute it in, because there was no way for us to measure directly the angular speed. So let's solve this for omega. Omega equals v over r. Right? That's what's going to be substituted into this energy equation. So let's take this guy, going in for omega. We still have to square it, but substituting in for omega. So I put in my k, mr squared, that's the moment of inertia I, and now I have, I'll just put in parentheses so you can see it, v over r, and squared. That's what that omega is. Okay, so let's make sure we distribute our exponents properly. We have 1/2 mv squared, translational kinetic, plus 1/2 k mr squared. Let's put this in blue to remind us this is our moment of inertia I. And then I have my v squared over r squared. Alright, and I'll put that in orange, or green. I'd been using green for my omega. Okay, so that's our omega right there. Omega. Alright, so I still haven't substituted any numbers. I've just decided to make k the variable to stand for the coefficient. Hopefully it's close to 2/5. So now I'm looking for k, so I want to solve for k. I want to make that the subject of my mathematical investigation, which is right here, this equality. So I want to isolate k. That's what I want to isolate and solve for. So let's see what I can do with this equation. First, I can see that 1/2 k mr squared times v squared over r, I'm going to have r squareds cancel out. So we measured the radius, but it looks like we don't need it. Scroll down a little bit. What else? I see some common terms. I see 1/2 and 1/2. I see m. Do I see any other common terms? Yes, I do. I see v squared, and v squared. So let's factor what we can and see how we can make this more manageable. mgh, initial potential, equals the sum of my kinetics, and I can pull out my 1/2, I can pull out an m, I can pull out a v squared. Distribute this, I have 1/2 mv squared times 1. Let's use kind of turquoise, light blue. Okay, so that's how I factored that. Plus, I pulled out from my 1/2 k mv squared, just above where I am now, I've pulled out the 1/2, I've pulled out the m, I've pulled out the v squared. So what am I left with? K. Right, I pulled out this 1/2, I pulled out this m, I pulled out my v squared. So I'm just left with k in fuchsia there, is all I got. Now I can see that if I divide both sides by m, then my m's go away. Now what are we left with? GH equals 1/2 v squared, 1 plus k. Okay. Now I said I wanted to solve for k, so let's do our order of operations properly. I have, multiplying both sides by 2, I get 2gh. Divide both sides by v squared, I get rid of my v squared. That equals 1 plus k. Let's bring it over here, just to the right side for our final equation. What does this become? 2gh over v squared minus 1 equals k. Alright, so here's, even before doing any experimentation or collecting data, I can come up with this and say, alright, this is what I need. This is what I need to measure. I need to measure g, well we know g already, 9.80 meters per second squared. I need to measure height, and I need to measure the final speed at the bottom of the ramp, v. And that's all the physical quantities I need if I'm just going to use this equation. And it's important for me to say this is the result of using conservation of energy. So I assumed some things in there. I assumed friction and air resistance were negligible. This equation tells us nothing about what k should be or what v will be, including energy dissipated through friction or air resistance. Energy that would be changed into heat or sound, for instance. Okay, but it's important that I say how I got this equation. So I have some measurements that I took. Here's an example. You've seen this before. I got my statistics for velocity, so I can find the mean, and I have the there are a few trials. This was actually only 2 trials. This is just an example of what that graph would look like if I see consistent data on my top chart, velocity versus time. See fairly consistent data. It's mostly a straight line. I'll highlight it and use the statistics function to find the mean. Now I have my other data from more trials, so I'm going to use the one. These were the 4 different ramps on that metal set of 4 ramps. I'm going to use the one boxed in red, 1.591. We'll round it to 1.591. That's how many digits are recorded actually in the measurements, and that's for the track that I use, because these are for 4 different tracks. So 1.591, you can see it boxed in red. 1.591 is going to be my v. That's my measured value v. It's an average based on multiple trials. I would say, how many trials did I do? How was I collecting this data? I used the statistics function to find the mean. So 1.591 meters per second. I made sure that it was in the right units. Alright, and it's important that I have it in meters per second because little g in my equation up here is in meters per second squared. So I need my units to agree. So let's evaluate our equation in the fuchsia box, given that we have a v of 1.591 meters per second, and I also needed to have measured h. So I did that, and it was about 18.5 centimeters, so 0.185 centimeters is the height I measured. And so now I have the data I need to evaluate for k. So I have 2 times 9.8 meters, 9.80 meters per second squared, but h0, I'm sorry, this is, I put 0.0185 centimeters, it's meters. It's 18.5 centimeters. I just wrote the wrong units for some reason. 0.185 meters, 2gh over v squared at 1.591 meters per second squared. So check out our units for a second. I have meters squared over seconds squared up top, and meters squared over seconds squared down below. So all of my units will cancel out. So let's get a number. Subtract 1 from that number, because I'm looking back at my equation in the fuchsia box. That should equal k. So k has no units. It's just a number, 2/5, 3/5. Okay, some constant of proportionality. So now we need to see what this is. What is this? 2 times 9.8 is 19.6. 19.6 times 0.185. We have 3.626. 3.626 meters squared per second squared divided by whatever 1.591 squared is. 2.53128. How many digits am I working with? I can float as many as I want until the final answer here. But I'll keep, what am I doing? 4, 1, 2, 3, 4, 2.531. 2.531. And this is velocity squared, so it's meters squared per second squared. So we see our units canceling out. I need to subtract 1. I get k. So I have 3.626 divided by 2.531. Excuse me. 1.433 if I round it. 1.433. No units left. They cancel out. Minus 1 equals k. Alright. So I don't need my calculator. 0.433 equals k. And I said k stood for that coefficient that appears before the mr squared. Go take a look. See our k right here? We said it stands for this coefficient, that fraction. So 2/5 is equal to 0.4. So that's what I said my standard was. If I write this as a decimal, 0.4. And I got 0.433. Okay, so my standard in pink is 0.4. 0, 0. I mean, it has infinite zeros. So if I were to talk about percent error, I would take the difference. I have k experimental minus k theoretical. I take the absolute value of that divided by k theoretical, that's the standard, and then I multiply by 100 to get a percentage. So let's find out what my percent error is. 0.433 minus 0.4 divided by 0.4, my standard, times 100. I got 8.25% errors. Alright, 8.25% error, and that was with some small wooden sphere. Okay, when I did it with a larger wooden sphere, this isn't the data I used. What was this? Was from a steel one, maybe? But I had 1.61 was another trial I did with a different sized ball on those metal tracks. If you remember the 4 black metal tracks that are all lined up, I had with a different trial, a different sized ball. I had 1.62, I think it was, or 1.6105. So there are various reasons that could be. Maybe as the ball rolls, and this is where we would talk about in our analysis and conclusion what could have contributed to the error. Maybe, yeah, there's always friction and air resistance, but maybe as the ball rolls down the track, it picks up some of the dust or, you know, oils. If people are touching it, there's something. Maybe the ball is getting something, it's covered in some of the dust is picking up, and maybe that changes the coefficient of friction slightly. Those tracks that are the black tracks that are just two, bent steel rods that make a shape, and it kind of cradles the ball as it rolls down. Well, I noticed if I use a much larger ball, it wobbles a lot as it goes down. So maybe those tracks and their shape and the width of the two bars between one another, maybe that width is optimum only for a certain size ball. Maybe after the ball has a diameter greater than 2 centimeters, it increases the unreliability of your measurements. Maybe the larger ball increases the error with that type of track. And that's something I could test. I could build a different track. Okay, maybe I use just a smooth wooden plank that doesn't have a groove or anything on it. That's another way I could try and investigate maybe how the diameter affects my measurement error, or the reliability of my measurements, the consistency of them, which would be a matter of precision. Of course, there are other ways we could investigate it and see from a different method how we could also find the moment of inertia. Right? If we had some way of rotating this solid sphere that didn't involve rolling it down a ramp. Maybe I use a turntable of some sort, or if you recall those two things I had found yesterday on Thursday and showed the class, they're two rolling devices that screw together, and you can put steel balls inside in different positions. Maybe using something like that would improve your results. It has a more fixed distribution of mass. You can actually see the mass inside. Maybe I want to try different, same size, but just different wooden spheres. Maybe they don't have a perfect distribution of mass inside of them. They're not really all that solid. One end or one area contains more mass than the other. There's a lot to talk about, and we need to say more about uncertainty and error in our lab reports. So here's one way to go through it. I decided to come up with this equation. All right, this is a decision I made to do, because I wanted to figure out, do I really need to measure mass and radius of each of these balls every time I'm trying a new trial? Well, no. If I'm using the ramp and conservation of energy, I just need H and V. Okay, so this is my way of being able to say, okay, I can do this efficiently by solving for what I want to find out. And I made that decision earlier just to use K as the variable to represent the coefficient. Alright, so that saved me from having to deal with the MR squared. I was able to cancel those out. If I immediately start substituting in measurement values, I lose that opportunity, because now I just have numbers there and I got to remember what they represent. And if I just have the variables, I can cancel out and create an equation to use. Alright, so there is one example. What else are we going to add about this? We need to talk about uncertainty and error. We need to, if we don't have we had an objective, right, which is determine the moment of inertia. So you don't have a hypothesis or a particular question. Make sure in your conclusion you're relating your final assessment of the lab back to the moment of inertia. Alright, so what did I get? 0.433 isn't the moment of inertia. The moment of inertia that I found experimentally, so I'll put I experimental to remind myself, is going to be 0.433. Not 2/5, but whatever 0.433 is. A little different. Off by 8.25%. That is my coefficient times mr squared. So let's say this wooden sphere that I used was, I don't know, maybe it's just 5 grams. Say I measured it on the scale and it was 5 grams. Well, I have to divide that by 1,000. 1, 2, 3. And I get 0.005 kilograms. 0.005 kilograms. Let's erase this guy. That's my M. I'm just making this up. I don't know what the M actually is. And then, let's say the radius was 2, or let's say the diameter was 2 centimeters, so that the radius would be 1 centimeter. We'll now have to divide that by 100, so I have 0.01 meters. Okay, so this is times 0.01 meters squared. So there's my coefficient, m and r squared. So that would get me my I. That's what I want to be able to say what the moment of inertia is. So let's, with my made up values, let's just see what that is. 0.433 times 0.005 times 0.01 squared, 2.17 times 10 to the negative 7. 2.17 10 to the negative 7. What units do I have for moment of inertia? I have a dimensionless quantity here. That's just a fraction of them. Kilogram meters squared. So that would be something I would place in the conclusion right there.